So we finished the numerical differentiation. Now it's numerical integration. Just on, well, the topic. So in the most general sense, we want to solve some kind of integral from a to b from the function f of x dx with some kind of call a quadrature of the function f. That's the most general solution we're after. Okay, so what is this beast, this numerical quadrature? It's basically just a fancy way of saying numerical integration. Quadrature. So, okay, so again, we will discretize the grid. So we assume that we have some points. Assume of PTS points. So A is going to be the first point, which is 0 less than x1, so on less than xm, which is endpoint, which is basically start A, B, we discuss it as x0, x1, x2, xm minus 1, oh, xm minus 1, and xm. Basically the points we're trying to use in our numerical quadrature. So, or the numerical, or A, I guess it's better. Quadrature given us. Basically, you're weighing the different points of function evaluations. K equal to 0. M the weights times F at all of these K's. So we can do the function evaluations. What we are really after is the weights. How should we weigh the different function evaluations such that we can approximate the integral? So the property here is that we want function to be approximated to of f plus, of course, some kind of error as a function of the function. Okay, and we also need a measure of how good this is, or degree of precision. Position. Called dp. So basically, it's if your quadrature can interpolate a polynomial of degree 2, then it has a degree 2 of precision. If it can interpolate a polynomial of degree 6 exactly, then it has a degree of 6. That's a basic idea. So in words, the O F of this quadrature positive integer, basically 0, or n is a member of, well, positive numbers, such that the error of this polynomial equals 0. I 0 for all polynomial pi of order I less than or equal to n. So pi, that's a polynomial of order I. So if our quadrature has a degree of position of 5, then it should be able to to exactly integrate polynomials up to order 5. So a polynomial of order 2, well, it can do that exactly, 3 exactly, and so on. A polynomial of degree 6, you're not, it could be that it's not integrated properly, or with some error. It could also be that you're lucky and are error. Could be, but you don't know, not general. Okay, so we'll have to start somewhere. So the trapezoidal rule, that's known, I hope. Trapezoidal, Simpsons, those are known. Well, some of you are nodding, so. So those are methods of estimating an integral. So we'll start with the trapezoidal rule and the Simpson rule, and we'll also look at the error of them. And then in later lectures, we will look at ways of using them in a better way to actually decrease the error. Some small tricks we can do with them, which I don't think you have covered in the earlier maths courses at NTNU at least. So, trapezoidal rule. Okay, so we assume that we have some kind of interval. That AB is divided into m subintervals. Oops. Sub intervals. I'll do a drawing later. And we will mark all of the subintervals x of k to x k plus 1. They will all have a width h. Maybe you can just draw this line. Okay, so we have our interval from, let's say, a over there, b here. That's our main interval, and then we have m subintervals. So 4, so four subintervals, and then we have k plus 1. Also, we have the width h equals b minus a divided by m, meaning that they are equidistant, or, well, the points are equidistant, the intervals are of equal length. So in all of these, this is 2 points. And then we can also write x of k will then be, well, we started a, so we can just have some kind of number k times or k 0, 1, all the way to m. Okay, then, given this, well, starting point, the trapezoidal rule is given as t is a function of function, and this with h is h over 2, well, we sum from a equals 1 m, so we note it says 1 down there, but I'll say that we start from k minus 1 plus f of a. What is this actually doing? Well, if we start with a function, okay. So what we're basically doing here is figuring out all the trapezoidals, and excuse my drawing. So we're figuring out all of the area in these trapezoids. That's why it's called the trapezoidal method. And you see, sometimes we are undershooting, so this bit over here, we miss it, and sometimes we are undershooting. But if you have infinitely many of them, your integration will be, well, perfect. But this trapezoidal rule, we can slightly rewrite it, which we will use later. H over 2. What I'm basically doing here is I'm picking out the first and the last function evaluations. So f of a plus f of b plus h sum from k equals 1 m minus 1 of x. Okay. Okay, so I'm not dividing on all of the others because, well, we're using 2. That makes sense. Okay. Questions so far? So, of course, we have to do the boring part, the error analysis. Well, no. Okay, so we'll start looking at the first interval, which is x0 to x1, and then we can generalize from there. So we'll see how much error we have in this first step. And if you sum all of the errors, then you get the total or global error. So, as a test, we will have a Lagrangian polynomial. So, 0 to x1, so that's the first layer of the function x dx. We say that this is c1, some kind of Lagrangian polynomial p1, x or x minus x0 x1 f twice times differentiated of some kind of xi x divided by 2 factorial, just 2. Okay, so why can I use this P1? Well, that's the same as the trapezoidal rule. So this P1 would basically be f of 0 minus x1 over x0 minus x1 x1 x minus x0 x1. So that's normal branch polynomial. And then we'll do some assumptions to make it easier for ourselves. We will assume that x minus x0 times x minus x1 doesn't change sign. Okay, so what does this mean? This means that both the points x0 and x1 are on the same side of the origin. So basically, if they're not, then we have to break down our problem such that we have some points to the right of our 0 and 2 points to the left. So that's why we can say that they don't change sign, because then we don't have to break up our problem. And also doing error analysis, we want to be pessimistic. We will also, for niceness sake, assume that this function f is twice differentiable continuous. That f, let's call it c. Is basically to say that you can differentiate f twice and it will still be a continuous function, so a nice function. Basically says that this thing exists. And in most cases, it does exist. So, okay. Next, we can use the mean value theorem on this. So we can write E 0 to x1 f x. The first one we can actually evaluate fully. X1. Then we have part f2 kind of constant c. One one two the x. So why could I actually put this function outside integral? That's the mean value theorem. It says there should be some kind of constant c such that this thing, such that this thing is equal to this thing for some c. You're able to pick a c. Okay, instead of using 2 there, I could be the same. That was confusing. I hope not. Okay. So next we can do a change of variables, and then we can try to integrate this. So we say that 0 plus ht says that dx equals ht, and where h same as that down here. Okay. Inserting all of this into the equation, we should end up with something. Can I remove this so it doesn't become as messy? Okay, so now I'm just going to do the insertions that are over there. We have that x0, 1, x equals h over 2. And then I use the shorthand notation for f's. 0 plus f1. So f0, that's f evaluated at the point x0. And while f1 is f of x1 plus this c. I'm gonna take the 2 outside, and we are stuck to integrating. Instead of integrating from from x0 to x1, we're integrating from 0 to 1 because of our transform over there. Okay, inserting, we see that we get ht times b h. No. dt. Okay. We can further simplify this. 1 plus, you see we have lots of h's. Have f twice derivative of some constant c, h3 over 2 to 1 t squared minus t. And this one we can actually solve. And we're stuck with 0 plus 1 minus c 12. And this then will be the error. Of the first interval. Okay, so this is only from x0 to x1, so that's only this interval. So what we have to do next is actually sum the error in each of it. But that should be similar to this. This is similar to the truncation error. Okay, so that means we do the full integral from a to b of x b 1 to big M. One k dx. Basically say we do it in small intervals. Okay, I just removed the rule down there, but we can repeat it. K equals 1 big M H2 F x k minus 3 12 times all of these f of k. I'm going to call them now because the constant will be different in each interval. Again from k 1 okay, and this is basically the trapezoidal rule. And up with h minus, reason we like to say that one of the, so that's the interval, plus h equals over m. 12 over m times the sum. 1 m so again, I've done a small rewrite here. See, this is h3, but h equals a over m, which is why this 1 over m here. This is kind of the average of the error in each step. Or just some number xi. So we say that we have integral from a to b, again, x t of f h minus a squared 12 f or used xi, didn't I? Yes. Some point zeta. It's just a point somewhere inside there. Color. So this, my error term, and it's of big O grid. Trapezoidal rule. Yep. Mm-hmm. Say again. let's see. I guess I also did something. So you are this. Is that what you're thinking about? Yeah. Okay. So you're wondering about this and this. Okay. So this is going to be kind of the average error. So I'm saying that there should be some kind of zeta which represent this average. Basically what I'm saying. But yeah, good question. So that's why you see the sum disappears and also the 1 over n disappears. Basically mean value theorem again. Say. Oh, so from here to here? Yes. Only that on paper you should specify where this is. I try to say it now, but I didn't write it on the blackboard. But if you do it on the exam, then you should just write why you could go from x case to just kind of value zeta here. Just mention it. That's why. So yes, you can do this on paper. Because I mean, this is the same as this. So if this is the same as this. But yeah, good question. Okay, so that's for the trapezoidal rule, which we will come back to later. To continue, we will use the Simpsons method. I'll not go as diligently through it, but, well, briefly explain it, I suppose. Can I erase the whole blackboard? Okay, start from scratch. Okay, Simpsons rule. If I can find. So what we're doing here, we're just gonna, this is just one interval, a, b. So if our function this, that's the function of x down there, then Simpsons rule. So this is one interval of Simpsons rule. Get there and there, and well, that wasn't bad. Okay. Let's say that it goes. Oh. There. Then instead of trapezoids, we will have parabolas in each of the intervals. See that h here will be between each points, but this is an interval. So in Simpsons method, we can actually do curvature as well. So it's fairly similar, only that we have two sub intervals. So if I have one interval here, you have two of sub intervals. So H will be A over 2m because of this, because you need more points. Okay, write it up. Simpsons of the function and some step length H over 3 m 2 minus 4 f of 1 f of a. Oh, correct. Again, I try to divide up the sums. H over 3 f a plus b. So I have to use notes for this, but getting everything correct is difficult. F of x 2k for h over 3 and sum 1 so yes, again, third form, basically taking this out. So f of a, first point plus lots of midpoints, k equals 1 minus 1 plus 4, k equals 1 m f x to k minus 1 plus the endpoint f of b. Those are the variations of Simpsons rule. Some of them I hope are known. Okay, so skipping some details. Following a similar error analysis as with the trapezoidal rule, we will end up with a to b x to x Simpsons rule minus some kind of error, b minus a f 4 times differentiated at 4 basically sum the trapezoidal error h. We'll be using this later to 12 And the error for Simpsons, which is A, F4, beats. So this is some kind of big O4, and this is ruler big O2. What is the degree of precision of both of these? Well, accurate up to the second degree, the degree of precision is 1 less, so 1. And for the Simpsons, the degree of precision equals third order polynomials. If you have a third order polynomial, you can integrate it exact using Simpsons method as a method with no errors. Any questions? One less. Here. Let's see if we can. Okay, so the error will be. So look at the Simpsons rule. So the error will be something 4 times differentiated. So if you have a polynomial of degree 4, you will have some kind of rest here. But if you have it of order 3, if you differentiate this 3 times, it would always be 0. Make sense? Yes? No? Yes, to have 100% accuracy, then if you're using Simpson method, you can only do third order polynomials. Let's say you have quick one, P3 equals plus x plus 1. So dx 3x squared plus 2x plus 1. 3 will have 6x 2, 3, well, just 6, x 4, 0, which is this. So that's why it has, so this is a third order polynomial, and you see if you differentiate it 4 times, just 0. That's why it's accurate up to this order. Okay. Then we have a 15-minute break.